So the next topic under our discussion is the arrangement of ions in ionic compound. So if you take an ionic compound, an ionic compound is also called ionic molecule. An ionic molecule is simply called as a crystal or crystal lattice. So when you go for ionic molecule and ionic compound is made up of one metal plus one non-metal. Metals are always cationic and non-metals are always anionic. So here that means this cationic and anionic species, they come closer to each other through the electrostatic force of attraction and they make up a bond, that is ionic bond, as we know. But before going to that, I'll give you a few examples of ionic compounds. If you take some examples of ionic compounds, sodium chloride, you can take magnesium chloride, aluminum fluoride, calcium oxide. All these are some of the examples of the ionic compounds. So what you are noticing here is, that is, let me say formation of ionic compounds, formation of ionic bond in ionic molecules using Lewis electron dot method. Formation of ionic bond in ionic molecules using Lewis electron dot method. So here what we need to understand is, suppose if I am taking the sodium chloride, one of the most important property in the formation of ionic bond in ionic molecules is, I am writing here, ionic bond is always formed because of transfer of valency electrons between two atoms. If there is a transfer of valence electrons between two atoms, then that bond results in the formation of ionic bond. Suppose for example you take sodium chloride, so I am taking sodium and I am also taking chlorine. If you take electronic arrangement of sodium, 2 8 1 is the electronic arrangement for sodium. Write the electronic configuration, that is 1s2 2s2 2p6 and 3s1. This is the electronic arrangement and electronic configuration of sodium. Go for chlorine, that is 2 8 7 is the electronic arrangement. Configuration 1s2 2s2 2p6 2p6 3s2 3p 3s2 3p5 3p5. Total number of electrons are 17 electrons, and here in sodium the number of valence electrons are 1, in chlorine the number of valence electrons are 7, 3s2 3p 7. What you are noticing here is, in sodium we have only one valence electron, but in chlorine we have 7 valence electrons, and moreover sodium is a metal and chlorine is a non-metal. So metals, because of less number of valence electrons, they lose the electrons. Losing here in ionic bond formation, losing here is nothing but transfer of that electron, that valence electron, from metal to non-metal. Metals can acquire stability by loss of electrons, and non-metals can acquire stability by gain of electrons. So if a metal loses, the lost electron is transferred to lost electron from metal, a lost valence electron from metal is transferred to the non-metal, which contains more number of valence electrons. So what you're noticing here, transfer of electrons, transfer of valency electron of valency electron occurs. So here this electron is being transferred from sodium, it is being transferred to chlorine. So therefore now you find that here sodium acquires 1 unit of positive charge with the configuration 2,8 of 1s2, 2s2, 2p6. Again chlorine, if you take here this chlorine, because of one electron from sodium being transferred to chlorine right now it has 7 valence electrons. By the electron which is being transferred from the sodium is taken away by the chlorine, and now the configuration, electronic arrangement 2, 8 and 8, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. I am underlining the valence electrons of chlorine, that is 3s2, 3p6. So here you are finding that here both the sodium in the form of cation and chlorine in the form of anion, both of them have acquired stability, and now sodium is a cation and chlorine is an anion. So the strong electrostatic force of attraction operates. The strong electrostatic force of attraction operates between Na plus ion and the Cl minus ion. So now if you want to actually define ionic bond here right now between the sodium cation and Cl minus ion, the strong electrostatic force of attraction which is binding the two oppositely charged ions, the strong electrostatic force of attraction which is binding the two oppositely charged ions in a molecule is nothing but the formation of ionic bond. Whenever you say ionic bond, there is no such bond between the two oppositely charged ions. Only thing is that the two oppositely charged ions, cations and anions, they come very close to each other and the electrostatic force of attraction operates. So they remain intact in the form of individual ions, that is cationic species and anionic species, they remain as individual ions, but the forces are strong electrostatic forces. These electrostatic forces itself, we understand it in the form of the ionic bond formation taking place in the ionic compounds. Similarly, if you take one more molecule for the formation of ionic bond in the given molecule, suppose as already I told you, the second example which I have taken is magnesium chloride. If you take magnesium chloride, there are 3 atoms available here in the magnesium chloride. If you take magnesium plus chlorine, 2 chlorine atoms here. So magnesium has 2, 8, 2 arrangement, electronic configuration 1s2, 2s2, 2p6, 3s2. So these are the valence electrons of magnesium, and if you go for chlorine, this is 2, 8, 7. 7 are the valence electrons. So 1s2, 2s2, 2p6, 3s2, 3p5. So 3s2 and 3p5 are the valence electrons of the first chlorine, and again second chlorine 2, 8, 7, again 1s2, 2s2, 2p6 and 3s2 and 3p5. You can see here again the second chlorine atom again we have 7 valence electrons. So magnesium, because it is a metal, it will try to lose these 2 electrons, and it forms these 2 electrons of magnesium, and the 2 electrons are transferred. Suppose I am going to take here 2 electrons, because it has 2 electrons, the 2 electrons I am going to show with the 2 dots in the form of Lewis electron dot structure. So if you consider the valence electrons of magnesium, valence electrons of 2 chlorine atoms, that is 7 and 7. So I'll give you the representation like this. Apply the Lewis electron dot method. So you take magnesium, chlorine, and chlorine. Here you have 7 valence electrons, here also you have 7 valence electrons for both the chlorines. First chlorine, second chlorine, magnesium. So for chlorine, for magnesium we have 2 valence electrons, so I am taking 2 dots over here. For chlorine we have 7 valence electrons each, so 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6 and 7. So 7 means I am going to take one more pair over here. Here also if I take 1, 2, 3, 4, 5, 6 and 7. So magnesium, if it wants to become stable, it is going to donate one valence electron to the first chlorine. I mean, it will transfer one valence electron to the first chlorine and another valence electron to the second chlorine. These are all valence electrons only, mind you. So the structure is going to become Mg2 plus and chlorine Cl minus. Here also chlorine Cl minus. So the strong electrostatic force of attractions operates between electrostatic force of attraction, strong electrostatic force of attraction. Electrostatic force of attraction operates here also. Electrostatic force of attraction operates between magnesium and chlorine. So finally we can take Mg2 plus 2 Cl minus ions, one magnesium carrying 2 positive charges and 2 chlorines carrying 2 negative charges. That will result in the molecule MgCl2 is the final molecule, that is ionic molecule in the form of ionic bond. So this is the ionic bond here. The strong electrostatic force of attraction operating between the magnesium cation and 2 chloride anions itself is understood in the form of ionic bond, and the molecule is becoming ionic molecule. After understanding the formation of ionic bond in ionic molecules, now let us speak something about, as already I told you, an ionic molecule is also called as an ionic crystal. An ionic crystal. An ionic crystal, sometimes it is also called as crystal lattice. Crystal lattice. What do you mean by the word lattice here? Lattice is group of oppositely charged ions, maybe cations or anions, arranged in three-dimensional pattern of crystal. Three-dimensional pattern of crystal. Actually, a crystal lattice is identified by the individual lattice points. These lattice points are also called structural motifs. These lattice points are also called structural motifs, which they move in the definite pattern, because if you go to a crystal lattice, the crystal lattice, because of its three-dimensional pattern. So when you speak about the structural motifs, these structural motifs are nothing but the lattice points in a crystal lattice. This crystal lattice, in fact, it is three-dimensional unit cell. So three-dimensional unit cell. When you say three-dimensional unit cell, this unit cell is having the 4 different types. This unit cell in the form of three-dimensional pattern as a crystal lattice has 4 different types of lattice points, that is BC, body center, FC, face center, then edges, E for edges, and C for corners. If you go for, again I am repeating, BC, body center, BC body center, FC face center, E for edges, and C corners, C for corners. So based on this, we can take one example for the crystal lattice. If you take sodium chloride, NaCl is a crystal lattice. Sodium chloride is a crystal lattice with the 27 lattice points. 27 lattice points in its unit cell. Unit cell is again a smallest portion of the crystal lattice, where it has the entire properties of the crystal. So if you go for sodium chloride, when you say 27 lattice points, this 27 lattice points